Hello and welcome to another tutorial. So this is the first part in a series of videos where we're going to be setting up a new behavior tree system. But importantly, what we're going to be doing there is taking the existing GOAP framework that we have, the goal-oriented action planning, and whereas before what we supported was state machine-based actions, we're going to add in support for behavior tree-based actions. And we'll also later on add in standalone behavior tree support. So with this, I am starting from a particular sort of point where I've already got a bunch of things already set up. So what I am going to do, if you're wanting to follow along with this, is in the description below, you'll actually find 3 links. The first link will be to the code as it currently is at this point in time when I'm starting the video. So if you're wanting to work from the exact same starting point I have, then that first link is the one that you're after. The second link will be the code as it is at the end of this video. And then the final link will be to the actual completed package. So by the time you're actually watching this video, the full set of all of this system will actually already be available there in the repository and there as a Unity package as well. Now with this, it's actually going to be spread across several videos. There is quite a lot that we need to get set up because we need to build our underlying behavior tree infrastructure. We also need to then be building up our actual behavior tree based actions and also our setup for the standalone behavior tree. So there's quite a bit that we need to get up and running. And because we want to have our AIs function in that same set of 4 scenarios, the first person one, the sort of simplified RTS setup where there's resources, the sim style setup, and then finally that village setup. So we want to be supporting all of those different scenarios. So there's quite a bit that we need to get up and running. Okay, so our initial thing that we're going to be getting set up is we're going to be getting up and running a lot of the core infrastructure for the behavior trees. And so I've already set up a folder here under the runtime section for our behavior tree. And initial thing I want to set up is our folder for our scripts. And we're going to have quite a few things that need to be set up here. So I'm following a similar structure to what I have for the other sections of code where I'm making a heavy usage of interfaces. And the reason there is that allows me to abstract things more and to keep sort of very clean interfaces there between things, which is really the overall point of them. So we are going to have enough of them that I want to actually group them separately. So we'll have our interfaces that define how everything connects. Now, in terms of what we have with interfaces, so for one thing, I want to actually have a interface for this idea of a general behavior tree. So interface for a behavior tree. Now within the behavior tree, that's going to be comprised of different nodes. And we're going to have a lot of different types of nodes. So what I'm actually going to do is I'm going to create one interface that every type of node supports. But then the 2 main types of nodes that we have is we'll also have flow nodes. So like the name suggests, a flow node controls how execution in a behavior tree proceeds. So this is where our patterns within a behavior tree of selectors or sequence nodes or parallel nodes, that would come under flow. So a flow node can link or can have children and typically will have children. But we'll also have action nodes, and an action node does a particular thing, but it cannot have children. So flow nodes have children, action nodes do not. So we'll have action node like that. So, okay, that's the main nodes that we want to be able to support. So we have our node, then off of that will come our action and our flow nodes. Now, within the behavior tree, on any of those nodes, we want to be able to attach two things, optionally. One is we want to be able to attach services. The idea of a service is it is something that runs and gathers information or performs calculations. So it's essentially a bit of a background worker. So I want to have a service interface. So we'll have IBTService. And the other thing we want to have is something called a decorator. So decorators, generally their purpose is controlling whether or not a particular node can run. They might also be used for setting very simple information, but their main purpose is to perform basically conditional checks of, okay, to run this node, you need to meet these criteria, and to enforce things like cooldowns. So we're going to create an interface for those. So I have IBTDecorator. Now, the one thing that I missed setting up, that I'm going to actually do right now, is in the root of our behavior tree folder here. What I want to do is I want to create an assembly definition called behavior tree. I want to make sure there is a root namespace set, like that. This behavior tree setup is going to need access to essentially the same things that our state machine one does. So our state machine one, if we take a look at it, it needs access to Common Core. So behavior tree, we're going to do the same thing. So I'm going to link that to Common Core and apply it. Now, because of creating that assembly definition after having created the code, I don't have these appearing as if they are in the behavior tree namespace. So that's actually going to be the first thing that I do, is as I convert these all over to being interfaces, I'm going to set them up to actually be within that namespace. Just keeps it consistent. So we're just going to do namespace and behavior tree. And then while I'm at it, I will clear out these, mark that as an interface. Now, things like our service, some of these ones will actually implement an interface to begin with. So in the case of service, it'll implement IDebuggable. So we want to enforce that every service has to actually do that. Our node, we do a similar process with it. So namespace, behavior tree, turn this into an interface. Now, using interfaces to the extent that I'm doing does incur this sort of extra overhead in terms of our setup process. That's okay, because the payoff is that it's easier and cleaner than if later on we want to swap sections in and out. That's really the big thing that we're achieving by using interfaces like this. So that's good. FlowNode we'll set up next as well. Make sure I cleaned up all of these. So our FlowNode again. Now for any of the other classes we create, because we've got the assembly definition set up, we won't need to do this extra step, but it's just for this first one that we needed to. Now flow nodes, I want to have them implement everything from INode, which will also bring in that IDebuggable. The other thing is that the flow nodes are going to have, the way they work with their children is going to differ potentially. So a selector and a sequence all can have, anywhere from 1 to whatever, essentially memory limits that we might run into are, because it's using a list for storing the children. But our parallel node, actually we want it to very explicitly only have 2 children. So I want to be able to handle that though generically for things external to our node. So what I'm going to do is, as well as saying that it implements the IBTNode, I'm going to also say that it has to implement IEnumerable. That will allow things outside of the flow node to iterate over the children easily. So it just makes that a little bit simpler. Decorator, we do the exact same things. So again, we put this in our Behaviour Tree namespace, like that. Turn that over to being interface. Our decorator only needs to implement IDebuggable. Most of the things that we are working with will implement that interface, so that's all good. Our action node is a little bit simpler. That actually just needs to implement our IBTNode one. So it's really only the flow nodes that had that extra complexity to them. So that's good. It's IBTNode. So we've nearly got all of these up to date. Behaviour Tree itself is an interface, and it also, unsurprisingly, implements IDebuggable and gets put into the same namespace. So I'm actually going to start with implementing these interfaces because they sort of represent the key relationships that the different things need to enforce. So our behavior tree is going to be the thing that our behavior tree based actions contains. So it will have something that implements this IBehaviourTree interface. Same thing for our standalone versions of the behavior trees will do that sit outside the GOAP system. This needs to be that sort of general interface through to the actual behavior tree itself. So there's quite a few things that we want to make sure that this provides. So one of the things is, well, common thing behavior trees are going to need to be doing is navigation. So we want to have our navigation interface there as a property that must be implemented. The blackboard, we want to integrate right from that very base point. We want it to be very, very easy for everything in the behavior tree to access it. So that's good. And the other thing that is going to be helpful, because we do at times need access to this, is we want to actually store the root node. Because the idea is that our behavior tree will have one root node, and then everything descends off of that. That root node, however, could be any of our flow node types. In theory, we could have it as an action node, but I want to go for supporting it just being a flow node. So, okay, that's good. Our behavior tree is going to need a way to initialize it. So we're going to need an initialization function that everything has to implement. And that's going to have to populate things like our navigation interface. It's going to have to also populate things like the blackboard. So that's good. And we also want to give control for being able to set the name of the root node, but provide a default just in case. We're going to have in root node name, which will just default that to root. That looks good. So that's an interface that must be implemented. In terms of other things that we need to do, well, we want to be able to add a child node to the root. So add child, actually I'll just call it, actually I think add child, make it very clear that it's specifically a child of the root node. So add child to root node. Now this could come in as any of our actual node types. So we want to make this a generic function. So that takes in a constructed node, and we restrict this so that node type has to implement a IBTNode. And what we will do is when we add the child to the root node, we actually also return the child. That just makes it easier for if we're writing our code where we are chaining things together. So that's good. That's sort of our setup things. We do need a reset function as well, because there will be times where we need to interrupt and reset the behavior tree. So we'll have our reset function. And then the final thing that we will have is we need to be able to actually tick our behavior tree. So when we tick it, we actually want to get a result back from that tick that indicates essentially whether it was sort of successful or not. So I'm actually going to define that in IBTNode here. I'm going to have a public enum, and this will be our node result. So there's a few different results that we could return back. One, if nothing has been properly set up, we should return back uninitialized. Otherwise, if it's properly initialized, then we should have ready to tick. That means it's ready for actually being ticked. In progress, if it is ticked and has still got further work to do, so for example, a node that's moving us to a location. Then we have succeeded, so it's finished, but finished successfully. And then we have failed. So similar thing, it's finished, but it actually failed in the process. So what we'll do is in our behavior tree, we will actually tick that and return that. So we'll have our node result tick in delta time. So that looks good for our behavior trees interface. That's all it needs to do. Let's look at some of the other things we need to get set up. We already started doing a little bit in Node, so this is actually a good time to finish adding things into Node. So a couple of other things that I want to be able to be doing. I want Node to have a fairly strict order of events for when it's ticking things, because when a node is ticked, a node has services on it, and a node has decorators on it, and your services might generate information that a decorator then uses that then causes the actual action of the node to be ticked. So there's a lot of stages to the ticking process for a node. So I'm actually going to set up an enum here, and this is going to be our node's tick phase. So what we will have is waiting for next tick. That should be sort of the state that we're in after, every time after we've processed a node. Then I want to split my services. So I want to actually have services that are always on. So these will be ones that get ticked essentially no matter what, as long as that path is active. Then I want to tick our decorators, because our decorators will control whether we actually proceed. Because then I will have general services, and those would only run if the decorators pass. Then I would have the node logic itself, and then, if there are any, it will tick the children. So that's good. We've got a very sort of strict phasing that we're imposing there, which will help. So common things that our nodes are going to need to be able to do. They're going to need to be able to access essentially this concept of self. So we saw that if you've watched the FSM videos or seen the code there is a lot of referring to self as in the owner of the behavior. So that is an interface that we want to make sure is supported. We want to have easy access to the owning behavior tree. Again, the blackboard is really important to just actually have that cached and have direct access to that. So we're going to keep track of that. Those are some key properties that we need to make sure that we've got there. Other thing that's going to be useful is storing the previous result. So the last status, and again, similar process there. Then we're going to set up a couple of sort of helper ones. So one of the ones will be, has it actually finished? So for it to be finished, the last status has to be equal to succeeded, or the last status has to be equal to failed. Either of those constitute a finished status. We want to be able to know if a node has got children. So that's going to be another one. Has children, because not every node will actually have children, because action nodes don't, but flow nodes do. So we're setting up a little property that will make it easy for us being able to handle that. So other useful things that we're going to need to be testing. So with decorators, they can block a node running, but then when they change to allowing it, we need to detect that. So I'm going to need to have an implementation for, do decorators now permit running? And this is something that will get run as part of the tick process and might need that information. So it's going to actually need to check, or need that delta time passed in. We need support for being able to reset a node. We need, obviously, support for being able to tick a node. So we will have tick, and we take in our delta time. Then I want to have a couple of helpers for being able to add a service. So this takes in an IBTService, and we also, with this, we indicate if it is always on. That we're going to default that to false. So we have our setup for being able to add a service and indicate if it's one of the always on ones. We're going to do a similar thing for being able to add a decorator. This just gives us a bunch of helpers to make this process easier. We have our decorator. Then the final thing we need to add is we want to add in an initialization function to make it easy for setting the owning tree. So what I'm going to do is create a function, set owning tree, and that's just going to take in our actual behavior tree so that we can link that up. So that's good. So that's for our node. Our flow node is largely, same. It's not really too much we need to add to it. The main thing is so on node, you'll notice we had support for adding a service and a decorator, but not for adding a children. So we want to actually only implement support for adding children to the flow node itself. So I'll have add child, and this will be a node. Let's call it in node like that. So that's good. So we can add a child to this particular node. So only our flow ones will support that. So that's good. Our action node actually currently doesn't need anything additional. It's good as it is. So we've got Behaviour Tree set up. We have our node set up. That's actually where there's a lot of the logic. Flow node and action node are all good. Then we've got our decorator and our service in terms of what they need. So we'll start with the service because it's a bit of a simpler one. So there's going to be some overlap with what the decorators and services and nodes have. In particular, being able to easily access self, the owning tree, and the blackboard. Those are needed by both. So we're just going to bring those over to both the service and the decorator. Now, for the service, the main additional things it needs is it needs that ability to set the owning tree. So we're going to bring that over as well. And then the only thing it needs on top of that is it needs a tick. Because a service doesn't actually need to know if it's an always on or not. That's handled by the node itself. So the service doesn't actually need to be implemented differently. The benefit of that is that with the same code, we can use the same service as either an always on one or as one where it's gated from a decorator. So that's really handy. So we have our tick. That's all we need for the service. Then if we go to the decorator, so decorator does need to be able to set the owning tree. Now there's a couple of things that the decorator does. One of the big things is obviously tick and then determine whether or not it should be able to run. So we will have a tick. Now this just returns a bool that indicates whether we actually can continue running. So it doesn't need finer grain than just yes or no. The other thing that we want to be able to do with the decorator is the decorators can be a chance to actually modify the return value from a node. But that's something that I don't necessarily need to have it be there for everything. So what I'm going to do is have a property that gets implemented, and this is whether it can post-process tick result. So that's something that a child of this or something that implements this interface will have to actually support. And then we need obviously the function that goes through. So how that will look is our node result. We'd go post-process tick result, and we give that in result. So it will take that result and it can then potentially modify it depending upon what it needs to do. So that's good. We've got our interfaces all set up for those particular elements. The other thing that we are going to end up needing, which I will set up the interface for it now because it's quite simple, is when we have a standalone behavior tree, we're going to need a brain essentially for it. So I want to define what that brain needs to look like. It's going to be pretty straightforward. So it needs to be a debuggable object. So not IDebuggable, which is for a component. An IDebuggable object is essentially a top level thing that's debuggable that we group things under. So each AI is a debuggable object, but the behaviors within an AI are debuggable. So it's just the slight differentiation there between these. So the only thing this actually needs to begin with is a linking of the blackboard. So linked blackboard, like that. So, okay, we have defined our different interfaces that we are going to support. And now we can actually start to look at getting these things set up. So what now we're going to do is we're going to start to get some of our base classes set up for things like the decorators, the services, the nodes, so that we've got something there to be building on top of. So first thing I'm going to do is we're going to create a folder for decorators. And then I'm going to create a new script. So this is going to be our base decorator. So decorator base. Now this is going to be an abstract class. And we're going to say that that implements IBTDecorator. Now, with this, some of the components that we're forced to implement, we want to directly implement them. Others, we're going to actually make them abstract so that the children of this have to implement it. So this is a pattern that I find works really nicely, of having an interface to define essentially the API, then a base class that takes care of any common logic for that, but is abstract, and then the concrete implementations from that. So in terms of with this, what I am going to do is let it actually have everything implemented, and then I'm going to go through and modify a bunch of these. So, okay, things like self. Well, that can actually go and say, hey, linked blackboard, get a game object, and I want you to get Common Core names self, like that. So that's good. The owning tree, well, I want to have that be concretely implemented, but I'm going to make it a protected set like that. Linked blackboard, well, I can say owning tree, linked blackboard. So that's good. Our can post-process tick result, that's actually one that I want to make that be abstract. And the same is true with this debug display name. So the reason for this is I want to force that children have to actually implement these. So the can post-process tick result, that just needs to be get, whereas the debug display name will be get, but with a protected set. So child classes will be forced to have to implement those two properties. Now there's a couple of additional ones that I want to actually add in. One thing is a protected bool for keeping track of if this is inverted. So, and actually we can make that public, but we'll make it a property. And this one I want to have it concretely implemented here. So the reason for having this is inverted is this gives us a really easy way of, say we've put together a condition and you're a decorator and it's working really well, but we just want to flip the result. So we want to be able to support that. So we're putting that in the base class so that it can be wrapped around, and it just means every decorator supports being inverted, which is super handy. It means we end up writing less decorators, which is always good. Less code, always better. The other thing I want to keep track of, and this won't be a property, and it's also going to be nullable, because we want to know if we've actually gotten this before. I just want to keep track of what the last result was, if we have one. So that's good. That's sort of the additional properties that we're going to need there. The other stuff then that I want to set up is I want to give this a constructor. Now, in terms of what this constructor takes in, all it's going to need to take in is if it is inverted, which will default to false. And all we do is just store that. So that's all we need for that so far. Our gather debug data. So we're going to follow a similar pattern to what we've done for other ones, where one of the things we'll do is put in an optional function that is our gather debug data internal that takes in the exact same parameters as our actual gather debug data function. But by default, we'll actually just do nothing. So by default, it's intentionally empty. Gather debug data though, that one we do implement. What I'm going to do is if it is not selected, then I'm just actually going to return. So we only log out stuff for the actual active one. Then what I want to do is, okay, well, if we actually have a valid last result, then we can use that information. Because I will, in our debugger, I will add a text line. And this is going to be, we just put Decorator. And we're going to then output wise. If it's inverted, then we, oops, this goes inside here. We put not before it, otherwise we just put blank. And then we output the display name like that. And then, because we know we've got a result, what we will do is like this. So we do the same logic. Now you might be wondering why I am wrapping these bits where I'm doing this ternary for text. The reason being is when you're using this sort of syntax of this string expansion, you actually find that you will need typically to wrap those conditional expressions. Otherwise, it tries to interpret the parentheses as formatting hints, and that obviously doesn't really work so well. That looks good. Added our text line, and we have to actually access value there. So that's why we added in that tracking of the value. Otherwise, it's actually a little bit easier for us, but it's very similar output. But what we do is we just say that it is actually not evaluated. There's a better description there. So it means when we look at this in the debugger, we can actually see, okay, is that decorator currently failing? Is it passing? Or has it actually not evaluated at all? Because that gives us the full set of info. And then we gather debug data internal, pass in the parameters so they just go through like that. So that's good. That's debugging support in now for all of our decorators, and the decorators can throw in additional information if they want. So really handy. So that's good. We don't have any default implementations for that, so that's fine. Now, in terms of our other sort of functions, our post-process tick result, well, that's one that children don't have to actually implement that. They don't have to override that. So what I will do is I will mark that as virtual, and its default behavior will just be to return the result. Straightforward. Setting the owning tree, well, we've actually got the owning tree property here so we can set it. And our tick, so what we want to do for the tick is say be last result, and I'm going to have a function that I haven't implemented or haven't created yet called onEvaluate, and that we provide our time. And then all I do is I return that, but what I check first is, are we inverted? If we are, then it's the not of that. Otherwise, it's just the actual value. So the final thing I do is we have a protected abstract, and this is going to be a bool. This is our onEvaluate. So onEvaluate that takes in the delta time. So we just want to force that children have to actually implement that. It's just going to keep it simpler and easier. So that's good. That's what our base decorator looks like. Let's go and set up something like a very simple decorator. So we don't want to have to actually implement a lot of ones, but let's implement a very simple one. So one of the types of decorators that I know I want to potentially support is a BTDecorator. And what this will do is force a result. So we're going to set this up so we can just see what it looks like. So we have decorator base, get rid of those. So this is a little bit cleaner and easier because there's less that we need to actually set up for this. So what I'm going to do is our debug display name. We do keep our get and our protected set like this. But what I'm going to do is just set that by default to force result. Now, can post-process tick result in this case is actually true. So in the onEvaluate, that actually is just going to always return true because it's not actually interfering with what's being returned. So it doesn't need to do anything further with that. I do want to have storing here a result to force. So what this will default to is succeeded. And then when we override, and what we're overriding is our post-process tick result. So we don't see that showing up. And that's because that function is public. So we actually have to do public override. We can't make it more restricted. We post-process the tick result, and all we do is we return that result to force. Then what I'm going to do here is give it a constructor so that we can easily configure it. So have our, not node result, BTDecorator force result. So it's going to take in a result to force. It's going to also take in an override for the display name if we're wanting to, and the ability to invert it. So B, and what I'll do is make these nullable. Is it inverted? Default that to null. We'll also have a string that's nullable, and this will be our display name. Like that. That's right, with strings, we don't need to. So what I'm going to then do here is, okay, well, result to force is that. So that's good. So, okay, we've got our result to false stored. What I would do is pass in that is inverted, so we can do base is inverted, and actually what I'll do is do like of that. So that's good. And then the display name, we only want to make use of it if it's actually been provided. So what I would do is, okay, well, if it's not null or empty, then our debug display name gets set to that. That's good. That's all we need for the actual forcing of the result. It's pretty straightforward in terms of what it actually has to do. So we will eventually set up other decorators, but this is sort of our basic one that we've got up and running. So, okay, that's good. We've got a basic decorator set up and with a base for that. Let's take a look at the services now. So let's set up our services folder. What I'm going to do is create C# script for service base. Now, it's not going to need too much. It is going to implement IBTService. It's going to be abstract. All of our base ones will be. So that's good. Tell it to implement everything. Now, in terms of self, we get to do the same thing we did for the decorator, where we get a game object and we're accessing that common core names and self. So that's easy. The owning tree, we have our get and our protected set like that. Our linked blackboard, we can get that from our owning tree. So that's easy enough. Our debug display name, we want to do our get and protected set, but we want to mark that as abstract, so children have to implement it. So that's good. The set owning tree, very easy. Like that. Tick, we don't need to do anything with. I will change the tick to return a bool though, just in case a service fails. That would actually be handy to know. So I'm just going to make that a bool. That's good. And then for the gather debug data, pretty straightforward again. I'm going to just steal from our decorator base because we want that same gather debug data internal. Now, the reason I go for this approach of having this gather debug data and we don't override it in children, we have this separate one, is because I want to enforce a consistent pattern for how the debug data appears and how it looks. So this makes it possible for me to easily do that. So similar thing of efforts not selected. We return. Oops. Like that. Otherwise, all we need to do is in debugger, we add a text line and we just output. This is a service. Its display name, like that. And then we run our little helper. That's all there is for a base service. Services don't really need a lot of actual sort of logic to them, which is really handy. So I'll demonstrate a very basic service. We'll just fix this error. So by default, a service will return true. Now the tick function for the actual service, that is one that actually, rather than having a return, I'm going to make it abstract. because there's no good reason to have a service where you don't implement tick. So I'm going to implement a basic service, so we've got an example. So one of the common ones that we need to be able to do is a service where we're getting essentially a location to move to. So calculate move location. So the context that we generally use this in is one where we are checking against navigation data, essentially. So we're needing to be doing that. So that's good. That's our service base. Tell it to implement everything. So there's not too much that by default we have to implement, which is kind of handy. But we'll get those, that, and we will just default this to calculate move location. Now this will actually have some standard values that it needs to keep track of. So we'll have a search range. It's going to need a threshold for recalculating. So this service is ideal for if you're doing something continually and recalculating where you need to move to, because it's also going to take in a system.func that returns a vector3 that corresponds to the location we're trying to actually sort of move to. So this is our get input location function. We'll get, actually it's kind of get requested destination. Because the idea is that this takes in a requested destination and figures out the nearest point on the navigation mesh to actually move to. So then it needs to keep track of our last requested destination. So that's good. Now constructor-wise, this actually needs quite a few things passed in. So we need to be providing in that search range. We need to provide in that recalculation threshold, but we're actually going to put the recalculation threshold later because that we can give a reasonable default for that. So instead, I'm going to have a system.func like that, just rename. So that's good. So I have a system.func that gets that in. I will also then have our recalculate threshold. And I'm going to default that to 0.1. So if we've moved by more than 10 centimeters, we will do a recalculation on the nav mesh. And then we support overriding the display name. So that looks good so far. So a lot of this stuff, straightforward. Search range gets copied over. Recalculate threshold gets copied over. Get requested destination also does. And then we check if that string is valid. And if it is, then we update the display name. So that looks pretty good. Now, in terms of what the tick needs to do, it's reasonably straightforward, and it's a pattern that we've used in quite a few places. So first thing we do is we get our sort of requested destination. So requested destination. So we run that function. Now, what I could do here is if get requested destination function is null, I return false, because if we don't have that function, there's literally nothing we can actually do. Then what I would also check is that move location that came back might be invalid. So if that matches our constants and our invalid vector3 position, we also return false because it doesn't have a location that's actually usable. We can't do anything with it. So what we can do is check, have we moved far enough to recalculate? So we calculate. So, okay, there's a couple of things we want to sort of check for this. If our, last, our last requested destination, if that is invalid, then we definitely need to recalculate. But we also want to recalculate if we've moved too far. So if move location, requested destination minus our actual sort of previous one that we requested, if the square magnitude of that is greater than or equal to our recalculation threshold squared, then we recalculate. So what I will actually do is I need to rename this, and I modify this here to be doing that. The other thing I will do is I will initialize our last requested destination to that invalid position, so it's properly set. So, okay, we've checked now if we have moved far enough to need to recalculate. If that's the case, then our last requested destination gets updated. And what we do is our requested destination, we're going to access our owning tree, the navigation interface, and we find the nearest navigable location. We need to provide self. We provide the destination, and we provide a search range. So that will give us back potentially a destination. So we're going to set that in the blackboard, and we set Common Core names, and this is our move to location, like that. And then all we do is return true. So this is sort of the structure that our services will generally follow. They'll do things in tick. We do still want to do error checking, but depending upon what we're doing, so as in the case here, I don't go and immediately sort of error out if this fails. I'll let it actually go through so other things can check that location. So that's good. We've got Decorator, we've got a service sort of set up there. So we've got a few of our sort of essential pieces that we need. One of the things that we haven't set up a base version of yet is a node. So I'm going to set up the rough structure for where our nodes will be. Now, this base node actually holds a lot of the logic. Like for the behavior tree itself, a huge amount of the work actually happens within this base node class. So this base node class will be the last thing I go through and we build today. The later parts of it will be happening in the next part in this tutorial. So let's get this set up. I'm going to have BTNode base. So this is going to do quite a lot. So we're going to have IBTNode like that. Clear out all of these, and we'll do our usual telling it to implement the things. So a couple of these are going to be pretty straightforward in terms of what we actually need to do. So our self is our usual linked blackboard, get game object, and our common core names self, like that. Our linked blackboard, to be able to retrieve that, we go to our owning tree, linked blackboard. The owning tree is something that will actually get explicitly set. So we can just do like of that for the owning tree. Our last status, so a few of these ones like that are all going to be things that are held internally. So last status will be like that. Oops. We'll do that so we can clean that up. That's good. So then for our has children and debug display name, first I'm going to mark this class as abstract because both of these I want to make them abstract. Child ones are going to have to implement those. For has children, all that needs to be is a get. For debug display name, that's going to be a get and a protected set like that. So, okay, so far so good. We've got our results, things like of that being stored. There are other things that we do need to keep track of. The last status, I will default that to uninitialized. What I will also do is keep track of the tick phase. So that one, other things shouldn't really need that. So I'm going to make this protected. So this will be our current tick phase. This is really more just for debugging purposes if something goes wrong. So I don't expect that we will end up needing to do anything much with it. It's just really a handy thing to make sure we've got it there for if we do hit errors, it's going to make it easier to track down at what stage in the process it's happened. So it's looking good so far. A couple of other things that we need is because this is going to store our services and decorators, but not the children. So this will have a protected list, and this will be our IBTService. So we have always on services. We'll have another list that is our decorators. Decorators. And then final one, and this is going to be our service. And what this will be is our general services. That's good. A couple of other things that we're going to need to keep track of if our decorators allow it actually to be running. So we'll have a protected bool. So decorators allow running. And we'll default that actually to false, because that'll make it very clear if something is wrong. Now for gathering the debug data, this is something where, okay, there's a bunch of stuff that we want to actually do with this. So we'll get to that in a moment. What I'm going to instead do is set up a couple of other things like, okay, setting that owning tree. That's actually something that is an easy thing for us to tick off. So owning tree is that. We can implement things like our add decorator and add service. So what I would do is our decorators list might actually be null. If it is, then we knew it, like that. Then I want to add that decorator in, but what I will do first is set its owning tree. That. Add the decorator, and what we do in terms of returning the node is we actually just return ourself. So we actually want to be returning ourself with this. So I'm going to modify, because we did it correctly for add service, but we did get it wrong with this. So we're just going to fix that up now. So that IBTNode like that. So that's good. So with our add service, well, okay, what we do depends upon whether it's an always on one or not. For starters, we can make it return this. It's straightforward enough. We can set our owning tree. And then what we need to check is if it's an always on one, then we also need to check if the always on services are null, because otherwise we need to new it. But then we can add it. Then the alternative is, okay, well, if general services is null, we knew it, and we added it. So, okay, we've got our implementations for adding a service, adding a decorator, and we're making sure we set the owning tree in every case with that, which is always good. Now we need to start actually getting, everything else happening with this. Reset is a pretty straightforward one for us to implement. Last status gets set to ready to tick. So, okay, tick is going to be one of the biggest parts of this and sort of one of the more complicated parts. So we're going to get that implemented. Now, what I want to do is also set up a couple of additional functions that can get run at particular points in time. So we're going to have a protected virtual void on enter. So this is when it enters this particular node. Now for now, they won't do anything, but we've at least got these interfaces so that we start factoring them in. So we also want to keep track of the concept of exiting a node as well, because there could be logic that we need to do for cleanup. So, okay, when we go to tick, well, first thing I want to do is if it was uninitialized, we reset it. So if the last status is uninitialized, we reset. So this will happen with the first time running. So we reset the node, but just prepares it. Then, okay, we want to set our current tick phase. Again, this is really just for debugging purposes, but it's handy to be doing this. So then what I want to do for the logic here for things like this is I want to actually wrap it. So I want to actually have a on tick always on services, and we'll pass in that delta time. So if that fails, then our status is failed. And what we do is we return. And again, because I need to have a few hooks into things, I want to have a on tick return, and we pass in that last status. So I want to actually be wrapping that return result. That's just going to make it easier for us substituting in logic that is checking that status, running it through decorators, things like that. So, okay, we tick the always on services first. And then we get to ticking the decorators. So this one is a little bit different in that, okay, well, we do an on tick and decorators, and we get the delta time. So, okay, we set our last status to failed. So far it seems very similar. But what we also want to check here is if this was actually a change. So if our decorators allow running, then we need to kick off triggering that we have actually exited this node. Now, there's a bit of logic there where we need to be able to know, have we actually started running the node and done anything? because we only want to send the exit if we've actually properly done anything. So I'm going to also up here, where we had our tracking of if decorators allow running, I'm going to put here a protected bool can send exit notification, which is false. And what I will do is then, remember these on enter and on exit. On enter has been called, then we can send this. And then we just reset that here. Because what I then do is I check, okay, well, if the decorators no longer allow running, but they did allow running, then what I want to do is send that exit if we can. So if they used to allow running and we can send the exit, then we will do so. So node has previously run and now is not permitted to. So that just allows us to make sure we send that on exit. We update that the decorators no longer allow running. And we again do our on-tick return of our last status, like that. That's good. Otherwise, our actual decorators do allow running. So we can set that to true. So that's good. We've kept track of if that status has changed. So, okay. Now, at this point, if this node is already completed, we actually shouldn't do anything further. So what I would do is it already completed? So have we already finished? So what we can do is check if we have finished. Then we just actually return we'll do our on-tick return of the last status, like that. And that's one where we could actually probably get away with just directly returning the last status, but we're going to not do that in this case. So that's good. So it's saying that it can't access that has finished. That should be working okay though. What we'll check is we are implementing IBTNode, has finished, should be fully accessible. So we'll see how that behaves once we've got a few other bits implemented, just to make sure that it's not just an error from it being confused. So, okay, we won't run a node if it's already done. So, okay, good so far. Then what I want to actually do is our current tick phase is we're going to set it to our general services, and we will check if those have failed. So if on tick general services, again providing our delta time, and this should follow the same pattern of, okay, if something has gone wrong, then we should make sure we fail this out. So, okay, what we would do is our last status is failed, and we return on tick return last status. So, okay, we've run the general services, we've run decorators, we've run our sort of tick logic. The other thing that I should be checking here is we've handled if our decorators did allow and now don't. But what if we actually switched from them being off, then that actually requires a little bit of logic that we should do there. And what we will actually do is do a reset. If the decorators have changed to permit running, then we reset the node. So that's really useful to make sure we've got sort of track of that being kept. So, okay, good so far. Now, we haven't sent the onEnter yet. So, node has never been ticked, which we can check that because our last status will be ready to tick. And if that's the case, then we run our onEnter. Now, the onEnter is something that our children can actually override. So if that onEnter fails, we actually might need to exit out immediately. So what we want to check is, okay, if our status is now finished. So if we has finished, then what I would actually do in this particular case is we would return our onTick return of our last status, because we know the node has actually already completed, so there is literally nothing for us to do. So that's good. Then we're now in the final sort of tick phase, almost. So we are now at ticking the node logic itself. So we would have a similar sort of thing to what we've done with other ones. So if our onTick node logic of our delta time, and then if that has failed, well, we do an onTick return, and we're going to end up actually making it that the onTick return can actually just set the status. So that will be an option that it supports. I'm going to just modify a couple of these because that'll just make it a little bit cleaner. So we really should only do this in a case where we want the status to be known. So this is one where it's appropriate because we're setting it to fail and then calling something that can be overwritten. Whereas something like this one, we can just fail it out as part of that process. So, okay, that's good. We tick the actual general node logic. If we get down to the very end here, we'll do our onTick return of our status, but our node might have children. So if it has children, then the current tick phase goes to being children. Also update the current tick phase here. We'll be waiting for next tick. So, okay, if we've got children, then onTick, and this will be our children in delta time. The key thing that we want to be sort of doing here then is we'll do our onTick return. We're not modifying the status. So we can just do our onTick return like that. So that's good. So we can start to implement some of these specific bits of logic. The onTick return we use a lot, so that's actually a good one for us to modify and get set up. So onTick return turns a node result, and it also takes a node result in. And this is our provisional result. So what we want to do with this is where if we have decorators that can modify this, they actually get their chance to run. So we have our final result, which will default to the provisional, and we return final result like that. So, okay, that's good so far. If we have decorators is the other thing we need to check. Is okay, if our decorators, and actually this is where I can move this, given that we wrap all of our returns in it. So if decorators is not null, then we can actually make modifications. And what we do is we loop through our decorators and we check, okay, well, if that decorator, and if it can post-process the tick result, then final result, we say decorator, post-process it like that. So it gives all of the decorators a chance to actually do their logic and running with it. Then what I want to do is handle sending of on exit potentially. So we need to check of if we can send the exit notification and do we meet the criteria? So which is has finished. So that's still getting grumpy and saying that that's not working, but we'll get back to that. So, okay, that looks good. We don't currently update the last status in this, so what we might end up doing is in a couple of places make sure we're properly sort of setting that, because we've kind of done a bit of a mix of how we actually work with this. So what I will say is things like the always on services, those will set it to failed, but we'll just do the on tick return of that last status. So that's good. What I would do is, it's fine for our decorators. We don't have really any other ones that we're actually needing to do this with. It's really just that initial one for the services, because we won't have actually done anything else at that point. Okay, so that's good. We've got our on tick return. We have our other functions that we need to actually set up. So we have our protected virtual bool and our on tick for always on services. It takes in our delta time. So the default for this is going to be to return true. And what we'll do is if we have always on services, then for each, and we check our service in our always on ones. And what I will do is if it fails, so we tick it, but if it actually fails, then we just abandon running any of the other ones. So we'll do this similar pattern with the decorators and with the general services as well. We want to make it that they only run until something fails. The second something fails, the rest stops. So it does mean that the order you put the services and decorators on something actually has meaning, which for decorators in particular is really useful. Now, whoops, that's not what I meant to duplicate. I am going to just copy and paste this because we do have very similar logic for general services. So it doesn't need to be any different. Whoops. Oops, if I get the name right for it. So that's our general services. Our decorators follow the same pattern. So our on tick for decorators needs to still check, okay, do we actually have decorators? but it uses the same tick logic and everything as well. So for our decorators, there's nothing different that we need to do. So that's good. So for our node logic then, we actually want to force the children to have to implement this. So I want to have our on-tick node logic, like that. And I want to do the same for the ticking of children, because this base doesn't have enough information to handle that ticking of children. So I want the actual child implementations to have to handle that. So that's good. We've got ticking of the node logic. We've got all of those ones up and running. Still getting grumpy about has finished. We will take a look at that in a moment. Because what I want to actually then do is the main remaining bit of code in this is implementing our gather debug data and things like of that. So, okay, our decorators checking if they need to permit, now permit running. So, okay, if they previously permitted running, then that's actually something where we don't need to do, any sort of checks here. Hasn't been a change. So what we're actually looking for specifically is a change. So if the decorator's already allowed running, then there's no need to check. So they can actually just run their normal logic. So we can just return false here. What we do want to do though is update always on services, because they could generate information that our decorators use. So if that fails though, so we'll do our on tick of always on services in delta time, turn false. So that's good. And then we want to check our decorators. So check decorators. So if any of these fail, then it's actually not valid. So if we get to the end here, then we know that we didn't previously allow running, but we now do permit running. So we can actually go and enable that logic. So that's good. Now for the gathering of the debug data, I do want to have that similar gather debug data internal. So I am going to bring that over. The difference here though is the nodes, I really need them to have a lot of flexibility for how they actually show the information. And I want them to be able to fully override the behavior. So I'm actually going to just pass this through. I think the main thing that I will only do is I will just check that it's selected. And even though I know that that means this has to be true, I'm not hard coding in true there, just in case later on I want to open this up to have more flexibility. Now, in terms of what the debug data here needs to do, there's going to be information for services, decorators, things like that. So I need to check, okay, if we have always on services. I need to check, okay, if we have decorators. And I need to check if we have general services. So each of those is going to need to do a bit of logic. First thing I will do is I will push the indent, and then I will pop it at the end. So I'm then going to loop over our services. So this is straightforward. It just needs to do gather debug data like that. Be the same logic here for decorators and for the general services. Just going to be a slight change in the naming, except for that one's fine. So that's good. This will make it possible for sort of controlling that output. Now, with this, I kind of don't want child ones to have to override all of this, but I want them to be able to override a fair bit. So what I could potentially do is restructure this a little bit. So these bits of logic happen here. And then this one happens here. But the problem with that, and I will actually undo this, is it gets tricky then between flow nodes, because this would mean that a flow node would be outputting the fact that that's the type of node it is after all of this stuff. And that may not necessarily be what we want. We might want those to appear first. So we're going to potentially need to change this around depending upon how we want this to look. So we'll leave it like it is for now, but this is something that we might find once we've got a few of the nodes and we're seeing what the debug display looks like, we might find that we want to modify how it actually looks and behaves there. So one issue that we do have is this has finished, really isn't behaving the way that we would want it to, in that it actually gets quite grumpy. It doesn't think that it exists, even though this is implementing the interface. And we don't exactly get particularly helpful errors. I'm going to bet, yeah, so its problem that it's having is it actually wants us to have this implemented. It doesn't allow us to have that sort of partial implementation in the interface itself. So what I'm going to do is I am going to change this like that, and I'm going to move that to just being a get like that. And then in our node base, alongside where I have our has children, I might actually do this above that. I will have that as an actual thing that's implemented, and that can be public. So that should make it less grumpy at us. Is an easier one because that's just a spelling error. So we can see that's now happy and building. So, okay, we have so far built up all of our interfaces. We've set those up. Those are pretty straightforward. There's not too much to each of those. We have set up our base decorator and a single instance of that. We've set up our service base and an implementation of one of those. And we've set up our base node, which is where a lot of the logic is. So that's those sort of core sections set up. Now at this point, it's nothing really we can sort of see. And this is sort of the challenge with stuff like this, is that there is a lot of infrastructure we need to set up. And it takes a bit to get those up and running before we can see things. So what will be happening is next time I will be getting set up more of the things there in terms of our flow nodes and more of our logic for sort of action nodes and decorators. So we'll get those set up so we can get closer to the point of actually being able to start implementing our particular bits of logic. But as I said, if you are watching this video, the full code for this is already available, and those links are in the description below. So if you just want to jump ahead to a later version of the code or the final version of the code, you can do that at any point in time because that code is already up there and available, and the package is usable right now. Thanks, folks. Hope you found the video interesting and helpful. If you have, check and like and subscribe. It really helps out. It's really appreciated. Now, if you're looking for the code for the project, remember there are 3 links in the description below. The first is the code as it was at the beginning of this tutorial video. The second is the link to the code as it is right now. And the final link is a link to the completed package that you have access to there. So you've got all 3 links available there, so you can jump ahead if you're wanting to. If you have any questions, chuck those in a comment below. And if you are looking for other ways to support the channel, then I do have Patreon, and there's a link to that in the description as well. But until next time, bye.